Okay, so I'm going to tell you about Flux. Again, on Monday, I'll give you more details. So this is just like the survival guide for what you need to know, but it's super easy. So you'll see that it's a lot easier than other things we have been doing. Let me just share my iPad. So essentially, this formula of flux that I'm going to tell you right now is basically only uh, for curves on the xy plane which are closed. So you should think of maybe a curve like this. So this is a type of curve that we have in mind. The idea is that, and again, this is something I'll mention later. You can think of this as a black box, but you know, you have to, when you move along a curve, you have to move with certain direction. So you sort of always move counterclockwise. I'm sorry. Okay. And then let's just recall that what was like the definition of work. Well, the definition of work was the integral of f dot v dt, or well, not really the definition, but the way in which we computed it at the end. Now, because it's a curve on the xy plane, the position vector is just x of t, y of t for a point on the curve, right? And so the velocity vector is just dx dt, dy dt, okay? And so if you think of the force field F as just being F1 comma F2, then really this integral can be written as the dot product of F1 comma F2 dot dx dt dy dt. And so really when you compute work, the integral that you're doing is F1 dx dt plus F2 dy dt. Okay, so this is the definition for work, or the way in which you can compute work in this case. Now, um, for flux, basically instead of, you still do a dot product, but instead of using the velocity vector, you use the normal vector. So think that the curve, at every point on the curve, there's some normal vector. And so the definition for flux is just the same integral that we had before of f dot, but instead of taking the dot product with velocity, you take the dot product with this normal vector. Okay, and so it all boils down to what's the formula for n. Okay, so again, the velocity vector was dx dt, dy dt, as you can see here. So what is n? Like, so this is a big question. What is n? Well, again, I'll say this more with more details on Monday. N is basically dy dt, comma, minus dx dt. And again, I'll check, we'll check on Monday that this is actually a normal vector. But if you believe this, then the flux, and this is a real formula that you need to know. If you do the dot product here, it would be the dot product between f, which was f1 comma f2, with n, which is dy dt minus dx dt. And so the formula for flux that you need to know is the following. Flux equals the integral from ti to tf of f1 dy dt minus f2 dx dt. And this gets integrated from over time. Okay, so again, like this, you just like write it or memorize it or whatever. So let's just do two examples so that you see it's not too bad. So this, and again, I'll repeat them on Monday. But imagine that you take a unit circle of radius r, and the vector field to be 2x minus 3y. Okay, so what is the flux here? Well, again, you use the formula. This is like f1 comma f2. So for these problems, you always need a formula for r of t. R of t in this case is r cosine of t, r sine of t, and the velocity vector is minus r sine of t, r cosine of t, and again, the vector n is dy dt, so this is r cosine of t, and minus the x dt, so it becomes r sine of t. And then the flux is just the dot product, again, between the force and the normal vector, not between the force and the velocity. So flux equals the dot product of f with the normal vector, which is r cosine of t, r sine of t, dt. This goes from 0 to 2 pi. And so you get integral from 0 to 2 pi of 2r cosine of t times x minus 3r uh, sine of t times y dt. And maybe just to sorry, just to make this a little bit easier, let's say that this is like this. Sorry about that. So I'm changing the formula a little bit. Okay. But then again, sorry, so just in case if you notice, I changed this to 2y comma -3. So you get 2y r cosine of t minus 3r sine of t dt. But again, the point is that before doing integration, you have to write y as a function of time, but y is r sine of t. So you get 0 to pi of 2r cosine of t times r sine of t minus 3r sine of t dt. Okay. And well, this is the integral of 2r squared. Well, this gives you sine square of t over 2 minus plus 3r cosine of t. And actually, this happens to be 0. So in this case, the total flux was just 0, and that's okay. Okay. Now let's do a slightly different example with a different vector field. Let's say that example 2. Okay, let's use this vector field, which is x comma y, and now let's say use a unit circle. Sorry, let's do it just for x comma for y. Flux for the unit circle. So again, you can say that x equals cosine of t. The parameterization of the circle is cosine of t sine of t. The velocity vector is negative sine of t cosine of t. And again, the normal vector. So the normal vector, what it does is flip the entries of the velocity vector and just changes the sign to the second one. So it just becomes sine of t. Okay. So to get the normal vector, take the velocity vector, flip it, and change the sign to the second entry of the normal vector of this flip. And so the flux is then f dot n dt from 0 to 2 pi, and then this is 0 to 2 pi of 4x comma 4y dot cosine of t sine of t dt, and this is 0 to 2 pi of 4x cosine of t plus 4y sine of t dt. But again, this is the integral from 0 to 2 pi of what is x. For knowing what x is, you have to go to the formula of the position vector. So x is cosine of t and y is sine of t. So you get 4 cosine square of t plus 4 sine square of t dt, and you get 0 to 2 pi of 4 dt, and you get 8 pi here. So in this case, there's a net flux. So again, we'll talk about the interpretation of what this means on Monday. Basically, like the way in which you should think about it is that in this second example, there's some fluid escaping through the circle, the unit circle, some mass being created. And in the first example, uh, there's as much fluid entering the circle as it is leaving. So on the net, there's no change in the amount of concentration that fluid that you have inside the circle. Okay, but again, the point is that the main formula that you need to know is this one. So once you know this, uh, the examples are pretty straightforward because you just do the integrals and get it done. So I'll explain this again on Monday with more detail.